let's look at another way to evaluate chemical data. And in this case, we're talking about significance tests. Now, there are several tests that we can use to explore more of what our data is and how it might relate to other data that we've collected. So let's look at one of those. One of those is the F-test, which is a very simple test. You just take the variance of one sample. In this case, I've noted it as the standard deviation squared, which is the same thing as variance, divided by the variance of another sample. Now, when you do this test, it's important that you put the larger variance on top so that this value is always greater than or equal to 1. Now, this is important because when we compare tabulated values in relation to the F-test, we always want to make sure that this is a value that's bigger than 1, because we're going to check to see if this test has produced a value smaller than what's in the table. And that would always be the case if we put the larger value on the bottom, and then we would be dividing by a larger number, and that would always make a smaller than the value in the table. So we always make sure that the larger value goes on top. Now, what does this do? Well, the F-test allows us to determine whether two different samples of data have the same variance or a different variance. And this will come into play when we start talking about the various t-tests. Now, t-tests are used to evaluate whether a particular method of measurement or two different samples are either statistically the same or significantly different from each other. So let's look at the two different kinds of t-tests. There's two major ones. There's a paired t-test, and that is where we have pairs of data points. And then we have an unpaired t-test, which is a more general option. So, paired. And an example of a paired, or the use of a paired t-test, would be having two different methods. Method 1 and method 2. And we're going to compare method 1 and method 2. So this could be a balance and another balance, or this could be a gravimetric method with a spectroscopic method. Lots of different things that this could be. But the important thing here is that we're going to take and measure a particular sample A in both methods. And then we'll take a different one or a different object and measure it in both methods. So sample B in both methods, sample C in both methods, D, and so on until we have however many data points we want. Now, again, the important thing is that I've taken the same sample and measured it two different ways, creating pairs of data, right? Now, if you look at the formula for how to actually manually calculate this t-test, it involves subtracting these two values from each other and then doing some things with the standard deviation of that, and it's not that important for what we're talking about here, because most of the time you'll have Excel or some kind of computer do that for you anyway. It's more important to recognize, oh, this is paired data, I should use a paired t-test. Or I need to evaluate this older method and compare it with a new method, right? I'm developing a new method. I want to make sure it's providing data that compares to what I would expect in this older, perhaps more time-consuming or complicated method. Then I would have the test to do that. That would be a paired test. Okay, next, as you may guess, if we have paired data, we could have unpaired data. So unpaired data. Now, with paired data, we don't have the problem of, oh, is this sample variance going to be different from one to the other case, right? Because I'm measuring the same sample in both cases. Over here, I could be measuring vastly different samples, right? And I could be measuring very similar samples. And how those are calculated is different based on whether they have the same variance or not. Now, we would evaluate whether they have the same variance or not by using an F-test. Once we have that, we'll divide this into equal variance and unequal variance. And again, the formulas change for this, but we're probably going to use a computer program to evaluate it anyway. We just need to perform this test first, then we can tell the computer program which particular formula to use. And in this case, we'll have sample A, and we'll be comparing it to sample B. Now, it's not important that these have the same number of measurements each, right? So I could measure sample A 8 times, and I could measure sample B 12 times, and I could still use this formula, an unpaired t-test, to do that. In fact, having a different number of measurements for each sample group is a very good indicator that you cannot use a paired t-test, because it just will not function that way. If you do have the same number of samples or same number of measurements for each sample, then you have to think through, okay, which t-test should I use? And again, if it is different samples measured and you're trying to see, are these statistically the same? Like, say I took water from a certain tap somewhere on the, in one building, right? And then I took water from a tap in another building, right? And I wanted to see, is there a difference between these two? Perhaps people were getting sick in one building versus another, right? Are these different sources of water? Is there a problem with those? Well, I would perform a t-test and I could see, oh, is it the water? Are these samples statistically the same, or are they different? Something like that could be the case. Now, while we're talking all about this, we should also talk about outliers. So, an outlier is a data point that we suspect has a problem. So we're doing all of our measurements and they're all clustering around one little point, and say they're all kind of in this range, and then we get one data point that's over here, right? It's definitely higher than the rest, right? Well, is it higher than the rest? Is it statistically higher? Because that's going to depend on the spread of this data. And so to really take some of our bias out of it, and we would like a more precise answer, and this particular data point is kind of messing that up, we should use a test to determine whether we can reject that particular value. Because we have to be careful when we're rejecting values, because it could be due to a bias, or it could be we want this data to look a certain way, so we should do a test. And one of the better test to do is a Grubbs outlier test. So here's a Grubbs value. You take the outlier value, subtract the average value, take the absolute value of that. So if it's negative, make this positive, and then divide by the standard deviation and compare it to values in a chart. If that value is smaller than the values in a chart, then we would retain this value. If that value is bigger, then we would know that this is statistically different from the rest. We can reject that value. Sometimes I've also used, is it outside of my 95% confidence interval that I've calculated? And that could be another way to do it. But the Grubbs test is probably the better of those two. All right, so these are just some of the significance tests and what circumstances we would use them for. And you'll just have to, for some of these, look up the formulas or use a computer to calculate them. And I would definitely recommend using the computer because sometimes doing these calculations can get rather tedious.